Welcome friends to the second part of the tutorial 3 in the course Basics of Mechanical Engineering 1. This course is co-taught by Professor J. Ram Kumar, Department of Design and Mechanical Engineering, and Dr. Amandeep Singh Roy, Imagining Laboratory. I am Amandeep. We have taken certain numerical statements in the previous lecture, the previous part of this tutorial on hardness, toughness, and static fatigue loading and critical loads. This lecture would be focusing on stresses in cylinders as spheres, buckling of columns, and Mohr circle we will try to shed some more light upon. Let us try to recall our concepts on the cylinders. Hoop stress, if you recall, in thin walled cylinders, that is induced with a cylinder having internal pressure within the cylinder and of radius r. So, P is internal pressure, r is radius of the cylinder, T is the wall thickness of the cylinder. We are talking about thin walled cylinder. Hoop stress is PR by T. And for a longitudinal stress in thin walled cylinder, you see the longitudinal stress along the radial direction. So, this is longitudinal stress. So, here this is sigma longitudinal, sigma L is equal to PR by 2T. The derivations of these were discussed by Professor Ram Kumar already. So, longitudinal stress which acts parallel to the length of the cylinder, internal pressure inside the cylinder is P, R is radius of cylinder, T is wall thickness, and practical implications were also discussed that this stress is typically less than the hoop stress, but it is crucial in determining the overall strength and stability of cylinder. Applications were given in the systems such as pressure vessels, ensuring that longitudinal stress does not exceed material limits. This is essential for safe and reliable operation. Also, Lammer's equations for thick walled cylinders were discussed, in which sigma r is equal to A minus B by r square and circumferential stress sigma theta is equal to A plus B by r square. So, where A or B are constants determined by the boundary condition of the cylinders, that is internal and external pressures and inner and outer radii. R is the radial distance from the center of the cylinder. So, these were already discussed in the previous lecture. So, these were already discussed in the theory lectures by Professor Ram Kumar. Let me take some examples here. A cylindrical pipe of diameter 1.5 meter and thickness 1.5 centimeter is subjected to an internal fluid pressure of 1.2 Newton per millimeter square. Determine longitudinal stress developed in the pipe, circumferential stress developed in the pipe. So, we are talking about a pipe and the thickness here is 1.5, diameter is 1.5 meter. So, thickness here is 1.5 centimeter and diameter is 1.5 meter. So, that means we are talking about a thin walled cylinder. So, here a dia of pipe is equal to 1.5 meter. I will put dia as D. Thickness T is equal to 1.5 centimeter, or this is equal to 1.5 into 10 raised to the power minus 2 meters. Internal fluid pressure this is P is equal to 1.2 newtons per millimeter square. So, as we know, the ratio T by D, that is thickness by diameter, this is equal to 1.5 into 10 raised to the power minus 2 by 1.5. This is equal to 1 by 100. So, because T by D is less than 1 by 20, comma, it is a case of thin-walled cylinder. Alright. Now here unit pressure P is given in Newton per millimeter square, and sigma 1 and sigma 2 will also be Newton per millimeter square. So longitudinal stress, that is the first question. Longitudinal stress, this is given by sigma L, this is equal to P into D by 4T. This is equal to, the value of stress is 1.2 into diameter is 1.5 by 4 into T. 4 into thickness is 1.5 into 10 raised to power minus 2. So this is equal to 30 newtons. Everything is now converted into millimeters. So because the pressure is given in millimeter square, so this also remains newtons per millimeter square. Right. Second part, circumferential stress. Circumferential stress, just to recall the formula, it is PR by T. So PR by T, it means because it is diameter given, so this becomes sigma circumferential is equal to P into D by 2T. It is diameter by 2 is R, PR by T. So this is equal to 1.2 into 1.5 by 2 into 1.5 into 10 raised to power minus 2. This is 2 times the longitudinal stress here, which is equal to 60 newtons per millimeter square. These are 2 answers that we have gotten. Let me see another problem statement in which a cylinder of internal dia 2.5 meter and thickness 5 centimeter contains a gas. If tensile stress in the material is not to exceed 80 newtons per millimeter square, determine the internal pressure of the gas. Here the unknown entity is P. Given is internal dia D is equal to 2.5 meters, thickness T is equal to 5 centimeters, which is equal to 5 into 10 raised to power minus 2 meters, and maximum permissible stress is given. Which is equal to 80 newtons per millimeter square. So as maximum permissible stress is given, so this should be equal to the circumferential stress. Circumferential stress, that means I say my sigma C, that is circumferential stress, is equal to 80 newtons per millimeter square. Right. So internal pressure of gas, if I need, I would just put the relation sigma C is equal to PD by 2T. So here what I have taken is, as we know that circumferential stress should not be greater than the maximum permissible stress. So we take the circumferential stress equal to maximum permissible stress. So it cannot exceed this value. So taking this value of the circumferential stress, I will put here as P is equal to 2T into sigma C by D, which is equal to 2 into 5 into 10 raised to power minus 2 into 80 by 2.5, right. So, here because again the value of stress is in Newton per millimeter square, I also will put the answer as 3.2 newtons per millimeter square only. So, these were very simple relations that we talked, and we try to just use the relationships of hoop stress, circumferential stress, the longitudinal stress to solve this problem. Let me see another problem statement. Here comes now a problem statement on spheres. Seamless spherical shell. The diameter is 900 millimeter and thickness is 10 millimeter, is being filled with a fluid under pressure until its volume increases by 150 into 10 raised to power 3 millimeter cube. Calculate the pressure exerted by the fluid on the shell, taking modulus of elasticity for the material of the shell as 200 kilonewtons per millimeter square, and the Poisson's ratio is 0.3. So, we need to calculate pressure exerted by the fluid on the shell. Here I will show you a relation. See, if d is diameter of shell and P is internal pressure, I would call it as intensity of internal pressure, and T is thickness, then we know sigma is equal to PD by 40, right. Now, here strain in any one direction, strain epsilon is equal to sigma by E, that is modulus of elasticity, minus sigma by ME, where 1 by M is our Poisson ratio. So, this is equal to, if I put the values, PD by 4 TE 1 minus 1 by M, this is equal to PD by 4 TE into 1 minus nu. Now, because the question is asking change in volume, let me also try to put that relation, change in volume, that is delta V. So, change in volume by original volume would be my volumetric strain. So, delta V by V, if I try to expand this, this could be put as V plus delta V by V minus V, right, plus and minus V. Now, here V is equal to pi by 6 d cube for sphere, V is equal to pi by 6 d cube, and additional volume V plus delta V, that is new volume would be proportional to the change in the diameter only. This is equal to, because diameter is only changed, I will put it as d plus delta d cube. So, let me put these values here. This becomes pi by 6, V plus delta V is d plus delta d whole cube minus pi by 6 d cube by pi by 6 d cube. This gives us a relation such as this is equal to 3 into delta d by d, that is 3 times the change in the diameter, that is strain is a change in diameter, this is equal to 3 times epsilon. Now, how is this coming? We ignored higher powers of delta d, because if delta d is suppose 0.001, higher power would be, square of it would be 0.000001 and cube of it would be 0.0, it is 0.01 into 10 raised to power, because delta D is, if it is very small, it is, suppose if it is 0.01, the higher power would be 0.0001 second degree. The third degree, it is cube, if it is, the third degree power would be 0.000001. So, it is 10 raised to power minus 6. We are ignoring the higher powers. So, we get it almost equivalent to, it is 3 into strain. Putting these values, we get delta V by V is equal to 3 into epsilon, and therefore, delta V is equal to V into 3 into epsilon. This is equal to pi P d power 4 by 8 TE into 1 minus nu, which is Poisson's ratio. This is change in volume. This is a kind of a derivation I have made here to be used in the given problem statement. So, change in volume would be directly used, this relation would be used to get the solution to this problem statement. Now, let me put the given values. A seamless spherical shell, 900 millimeter diameters, D is 900, T is 10, and delta D is 150 into 10 raised to power 3 millimeter cube. Modulus of elasticity is 200 kilonewtons per millimeter square. Poisson's ratio is 0.3. So, let me put all these values here. So, we have D is equal to 900 mm, T is equal to 10 mm, delta V is equal to 150 into 10 raised to power 3 millimeters cube. Modulus value is 200 kilonewtons per millimeter square. This could be converted into newtons, that is 200 into 10 raised to power 3 newtons per millimeter square, and I have value of nu as 0.3, that is 1 by m. Now, question is, what is pressure exerted by the fluid? So, P is question mark. Now, let me try to calculate this. Directly putting all the values in the given relation, we know delta V change in volume is equal to pi P d power 4 8 TE into 1 minus nu. This is equal to pi P D is 900 power 4, then 8 into thickness, that is 10 into value of E, that is 200 into 10 raised to power 3. Delta V value is also known, that is 150 into 10 raised to power 3. This into 1 minus nu, that is 1 minus 0.3. This is Poisson's ratio. This gives me P is equal to 150 into 10 raised to power 3 by calculating this whole value on the right hand side. So, this is 90190. Therefore, P is equal to 1.66 newtons per millimeter square. So, this was solved depending upon the values which were given. These values were given: Poisson's ratio, modulus of elasticity, diameter, thickness, change in volume. So, change in volume, this relation was here derived from the circumferential stress, were derived from the longitudinal stress and the strain for spheres. So, these were certain problems, cylinders and spheres. Let me now try to discuss columns. In columns, you discussed about the slenderness ratio, we discussed about the crippling stress or the radius of gyration. I am coming directly to the problem statement. Calculate Euler's critical load for a stud of T section, the flange width being 10 centimeter, overall depth 8 centimeter, and both flange and stem are 1 centimeter thick. The figure is given here. The width of the flange is 10 centimeter. The overall depth is 8 centimeter, it is given, and flange and stem are 1 centimeter thick, it is also given here. The stud is 3 meter long and is built at both ends. So, this is the cross section of the stud. But this is 3 meter long. Now, let us try to understand or calculate the moment of inertia about the x-axis or y-y axis. It is given here, this is x-axis axis and this is y-y axis, and try to then calculate the critical load. So, you have been given length is equal to 3 meter, that is equal to 3000 meters, and E is given 2 into 10 raised to power 5 newtons per millimeter square. So, recalling the concepts of moment of inertia. So, moment of inertia, if we need to calculate, we can see this is symmetrical along y-y axis. So, y-y axis has symmetry. So, CG lies on y-y axis. CG, that is center of gravity, lies on y-y axis. So, here y bar is equal to distance of CG of section from bottom, right? From the bottom end, the distance of CG would be y bar. Now, we know for flange, area is given, small a 1 is equal to area of flange is equal to 10 into 1, that is 10 centimeter square. And if I take y1 as distance of CG of area A1 from the bottom end, distance of CG of area A1 from bottom end, this is equal to what? Distance of CG from bottom end, I have to calculate it here. This will be equal to, total is 8 centimeters. This is 8 centimeter, this is 7 centimeter. So, total distance here is 7 centimeter, here 7 centimeter plus half of the flange length. So, it will come somewhere here, that is 7 plus half of 1 by 2, 7 centimeters plus half of 1. So, that is 7.5 centimeters, that is somewhere here. This is the plane on flange. This value is 7 centimeters and this total value is 8 centimeters. So, in between 8 and 7, at the mid of the 8 and 7, the CG lies. So, similarly for the stem or web, this was for flange. Now, I will put for stem or web, I will put A2 as area. This is equal to 7 into 1 is equal to 7 centimeter square. and y2 similarly is the distance of the CG of area A2 from bottom end. So, this is equal to 7 by 2 is equal to 3.5 centimeters. Now, using the relation for y bar is equal to A1 y1 plus A2 y2 by A1 plus A2. This is equal to 10 into 7.5 plus 7 into 3.5 divided by 10 plus 7. So, I get the value of y bar as 5.85 centimeters. So, let me continue this problem in the next slide. Now, here y bar is gotten. Now, let us calculate moment of inertia about x and y axis. That is, moment of inertia x is equal to the two areas here. So, 10 into 1 cube by 12 plus A1 into 2.15 minus 0.5 square plus for the other section 1 into 7 cube by 12. We are talking about a rectangular section here. A2 into 5.85 minus 3.5 whole square. So, this Ixx value is calculated as 95.298 centimeters square. Similarly, we calculate Iyy, which is equal to 1 into 10 raised to power 3 because it is very symmetric here. So, this by 12 plus 7 into 1 cube by 12, this is equal to 83.916 centimeters per 4. This. So, least value of moment of inertia, is for Iyy. Therefore, I is equal to 83.916 centimeters power 4. Power 4 is just multiplied by 10 power 4 and convert into millimeters. 839160 millimeters per 4. Now, effective length, that is L effective is equal to L by 2. This you should recall, this is equal to 3000 by 2 is equal to 1500 mm. Right. Now, Euler's critical load P is equal to Euler's critical load, this is equal to pi square EI by effective length square. This relation also you should note. The references are given for Euler's load. So, this putting all the values in the relation. So, we get pi square into E, that is 2 into 10 raised to power 5 into value of I, that is 839160 by effective length square, that is 1500 square. This gives me the value of P as 736.19 kilonewtons, which is my Euler's critical load. This is the answer. Now I will try to come to the Mohr circle directly. Mohr circle, if you recall the concept of the Mohr circle, there were certain rules that shear stress tau is negative when we move in clockwise direction and it is positive when we move in anti-clockwise direction. Similarly, sigma normal stress is negative when we talk about compressive load and it is positive when we talk about tensile load, right? And value of theta is always 2 times. Why? Because here theta is equal to 90 degree. In the case of the Mohr circle, it is circle. Here theta is 180 degrees, right? So therefore, third rule is theta is always taken as 2 theta. Now, taking all these rules or the principles of Mohr circle, let us try to solve this problem statement and try to understand how do we draw the Mohr circle. Now they say the state of a plane stress at a point is represented by stress element below. This is given here. Find the stresses on an element inclined at 30 degree clockwise and draw corresponding stress elements. So it is 30 degree clockwise rotated here. This angle is 30 degree, you can see here, and we need to find the stresses. Though they have found the stresses while putting the relationships of the stresses, all the stresses are found here. 25.8 megapascal is sigma x1 and 68.8 is our, this is coming in perpendicular direction from up coming down 20. So this is our tau x1 y1 and 4.15, this is sigma y1. Talking about the Mohr circle here, we know we have the normal stress in this direction and the shear stress in the y direction, it is tau. Let me first try to plot the points A and B here. A is sigma x tau xy. In the x direction you see the load here is compressive because this is moving in this direction and opposite direction 80 megapascal of compressive load. So therefore it is negative. Therefore minus 80 and tau xy, the 25 megapascal is the value here and it is in the positive direction for a compressive load. So I will put 25. Similarly, point B could be plotted here, sigma y tau xy, and sigma y, if you see, the load is 50 megapascal and this is tensile load. Because this is tensile load, this will go as 50 as positive value, and here this is minus 25 value of tau xy. Let me try to plot these points here. The point A is minus 80 and plus 25, it comes almost here. So let me say each pointer is around 20, 20, 40, 60, 80. Similarly here I will put 20, 40, 60, 80. 4 pointers I have divided. So to calculate 25 as well, I will put 20, 40, 60, 80 somewhere here. Again 20, 40, 60, 80. So to draw the Mohr circle, point A would be plotted minus 80, 25 here. It is minus 80 here and 25 is somewhere here. So this is my point A, that is minus 80, 25, right. This I am as well, this as of now I am talking about at theta is equal to 0, or I will put it as theta is equal to 0. No rotation is there as of now. And point B is 50 and minus 25. So x 50. So somewhere here 20, 40, somewhere here 50, and minus 25 would be somewhere here. This is my point B. This is 50 minus 25. So these 2 points, if I try to join them, and the midpoint here would be center. How to find the midpoint? Otherwise, I can just 25, 25 is cancelled. So it is midpoint. I will put this point as my point O, or origin, right. So this point, if I wish to calculate it, it would come as O would be taken as minus 80 plus 50 by 2. That is, original is calculated, center is calculated as sigma x by sigma y by 2. This is what? This is sigma x plus sigma y by 2. So this value is minus 15. So almost in a perfect circle it would be at minus 15 point here original. So this is not important. The point that is more focused here is, so we have gotten the center somewhere here, right, and we draw a complete Mohr circle using this as center, and then we try to rotate it by 30 degrees. So let me try to draw the Mohr circle. This is a manual drawing, means without using a compass or anything. I also didn't use any circle in the PPT presentation here. So please bear the small changes in the geometry if those are there. So here the angle given is now 30 degrees. So 30 degrees, as I have given it to you, the theta becomes 2 theta. My theta value becomes 2 theta. 2 theta is equal to 30 degrees clockwise is given. So I will put it as 60 degrees. So at an angle of 60 degree from here, I will draw a line. So this is 60 degrees, or you call it minus 60 degrees from there in this direction. And this is our theta, it is given theta 1. And if I try to draw a straight line here, it will come somewhere here. This is my point D. These are my points C and D, where C is having theta as minus 30 degrees and D is having theta as minus 30 plus 90 degrees. Now what I am missing here is the theta 2. Theta 2 value here is, this is 2 theta 2. Now I can calculate all the stresses values which are required here, corresponding stress elements, that is sigma x1 is equal to O minus R cos of 2 theta 2 plus 60. I can locate this value here. So this is my value of sigma x1 in negative direction. Sigma x1 value is given. Now sigma x2 is O origin plus R cos of 2 theta 2 plus 60. You can see it is just getting added and subtracted. This value is getting added and subtracted here. So just plotting it on the Mohr circle itself, I can calculate these values. And also tau x1 y1 is equal to minus of R sine of 2 theta 2 plus 60. So this value of sigma x1 comes out to be minus 26. Sigma x2 comes out to be minus 4 and tau x1 comes out to be or minus 69. Now you can see how close are these values. Just look at these, minus 26 and 25.8 megapascal, minus 4 and 4.15, and then you see minus 69 and 68.8 megapascal. This is without using any equations or so. Mohr circles gives us, using the plot itself, the values of the corresponding stresses, and we have calculated those here. Only certain rules which are there for the Mohr circle, we have used them. Though I have put these components here for sigma x1, that is O minus r cos 2 theta 2 plus 60. So, where is r? R is the radius of the Mohr circle. This is r here, this is r here. To explain these components, r cos 2 theta plus 60 and r sin 2 theta plus 60, I will just draw two triangles here. So, this is a triangle. I have put this point as O. Let me say this origin is O1, right. So, this number is capital O, big O, this is big O here. So, I will draw two projections here, one from point C down to normal stress and another from point D to normal stress, these two projections. So, here if I try to draw this, this is O, this is D, and this angle is what? This angle is 2 theta 2 plus 60, right. And this point that is here is our sigma x1, that is, here I have my sigma x1 here, this is my sigma x1 here. Similarly, this point is sigma x2. So, here this is 2 theta plus 60 and this component O sigma x1, make sure that this is small o, I will put it as small o here, this is small o, this value is big O. So, this is equal to this component, because this is r. So, this becomes r cos 2 theta 2 plus 60, right. Similarly, this component is r sin 2 theta 2 plus 60, and for the point sigma x2, we can draw another triangle here once again. This is projection on the line, this point is C, right. This point is sigma x2 and this is my O, and this angle is again 2 theta 2 plus 60, this is my r, the radius. So, this becomes r sin 2 theta 2 plus 60, and this component is same as r cos 2 theta 2 plus 60. So, which means my sigma x1 value, this is when we subtract r cos theta 2 plus 60 from O, this is O, right, and sigma x2 is when we add O and r cos 2 theta 2 plus 60. Now, I am left with only tau x1 y1. Tau x1 y1 projection comes here. I will put that in blue color only. This is tau x1 y1, which value, this total value this is equal to r sine 2 theta 2 plus 60, and this is negative here because shear stress is negative above the normal stress line. So, this explains the complete Mohr circle. I think this numerical would help you to understand the Mohr circle completely. Let me take some more examples here to explain it further. So, here it is given principal stress is sigma 1 as 54.6 megapascal, sigma 3 as minus 84.6 megapascal, and element in the plane stress, that is sigma z is equal to 0. So, the other principal stresses are also 0. So, this is a case of a 3-dimensional Mohr circle where sigma 1, sigma 2, sigma 3 are calculated, and it is always sigma 1 is greater than sigma 2 is greater than sigma 3, which means sigma 1 is always largest and this is always smallest. So, here it is given sigma 1 is equal to this 54.6 megapascal, sigma 3 is equal to minus 84.6 megapascal, and sigma 2 is 0, let us say. So, now we can draw 3 Mohr circles with these values, and it could be something like this. In Mohr circle, you also know this principle that it is always negative shear stress here in the above the normal stress, and below the normal stress line it is always positive shear stress. We know sigma 3 is the minimum value and sigma 1 is the largest value, and since sigma 2 is equal to 0 here, so this is my sigma 2 here already 0, and if I say divided into 84.6 is there, I will divide it into 5 parts till 100. So, it is 20, 40, 60, 80 and 100. So, here also 20, 40, 60, 80, 100. So, 20, 40, between 40 and 60, my each increment is increment on axis is equal to 20 megapascal. What are these drawn here? So, here between 40 and 60 I will get my value of sigma 1, which is maximum, that is 54, it is here. Sigma 1 is equal to 54, and here if you go behind just close to 80 I get my value of sigma 3. So, I can draw 2 Mohr circles here in between a bigger Mohr circle. So, this represent my Mohr circle. I can again plot the pointers here. So, this means 3 Mohr circles can be drawn each based upon 2 principal stresses. So, that is here principal stresses, we can say either sigma 1 and sigma 3 is representing one circle, it is bigger circle, I will call it circle 1, that is circle 1, then sigma 1 and sigma 2 is giving me another circle, sigma 1 and sigma 2, this is circle 2, and I have sigma 2 and sigma 3 as another circle, which is my circle 3. So, which means 3 Mohr circles can be drawn based upon the 2 principal stresses. Continuing this problem into a volumetric form if I wish to represent them. So, this is all the stresses which are given here, right. Only I have given sigma 1 and sigma 3 here, sigma 2 is 0. So, Here this is a volumetric representation. So, because this is a Mohr circle already given, let me try to draw individual two stresses here, principal stresses. This is a tensile stress going in opposite direction, sigma 1, and a compressive stress in putting load inwards, that is sigma 3, right. So, that means there are two stresses here, one is sigma 1, that is tensile, and I have sigma 3, that is compressive. Now, the last problem has a Mohr circle already given. It has the tensile stress sigma x and another tensile stress sigma y. Because both of them are tensile, you can see both of them are on the right side of the origin. Right side of origin, that is all of them are positive. Now, also it is given tau y in the anticlockwise direction and this Mohr circle is given. So, we need to find the maximum shear stress. Here, how do we calculate maximum shear stress? Simply tau max for 1 and 2. So, for 1 and 2 we have stress 1 and stress 2. It is sigma 1 is maximum here, sigma 2 is in between, sigma 3 is minimum. So, tau max would be here sigma 1 minus sigma 2 by 2. So, this is given here. Now, tau max for 2 and 3. This is what? This is sigma 2, that is the larger stress minus the smaller stress, sigma 2 minus sigma 3 by 2. So, what is value of sigma 3 here? It is 0. Sigma 3 is equal to 0. So, that means this tau max for the 2 and 3 is only sigma 2 by 2. Similarly, the shear stress for the larger circle, that is for 1 and 3, this is equal to sigma 1 minus sigma 3 by 2. This is again sigma 1 by 2. And what is the overall maximum tau? Maximum tau value is sigma 1 always. So, what is the overall maximum tau value here is? Maximum tau value is this sigma 1 by 2. So, I would put here as overall maximum tau, that is tau max. I will put overall, this is equal to sigma 1 by 2, the largest value. With this, I am closing this tutorial and we will meet in the next week where we will discuss the laboratory demonstrations on the solid mechanics theory and tutorials that we have discussed in the previous weeks. Thank you.